This week in 241, we'll be talking about Faraday's law. What is Faraday's law? Faraday's law states that a changing magnetic flux will induce an electromotive force in a closed circuit to oppose the change in flux. Perhaps we should take a couple steps back. Let's start by defining flux. Magnetic flux is the dot product of the magnetic field and the area vector. The area vector points in the direction normal to the surface through which the magnetic field passes and has a magnitude equal to the surface area. The angle for the dot product is defined in the way pictured here. You can think of the flux as a quantification of the amount of magnetic field that is able to pass through the surface. From the equation, the magnitude of the magnetic flux is at a maximum when the area vector and magnetic field vector are parallel, which is when you will have the most magnetic field able to pass through the surface area. The magnitude of the flux is at a minimum when the area vector is perpendicular to the magnetic field, which is when none of the magnetic field can pass through the surface area. We can change the flux in three different ways. The first method is by changing the magnitude of the magnetic field. We will use this method to change the flux during this week's lab. The second method is to change the magnitude of the area vector. The third method is by changing the angle between the area vector and the magnetic field vector. We will use this method extensively during next week's lab. Now, let's return to Faraday's law. Let's use an example to help understand what it says. If you put a current through one set of coils that are wound counterclockwise as you go up toward the top of this image, we can use the right-hand rule to determine that a magnetic field will be generated up through the coil. If you put a second set of coils next to it, the magnetic field will go through the second set. Now, if that magnetic field is increasing, the second set of coils will try to oppose that change in flux by generating its own magnetic field in the opposite direction. Once again, using the right-hand rule and noticing that these coils are wound clockwise as you go up toward the top of this image, we can determine the direction that the current must be flowing through the second set of coils in order to generate this magnetic field. The electromotive force, measured in volts, is the energy per unit charge needed to generate this current. Because there are n loops of current, we need to take this into account in our equation by multiplying by n. By plotting flux as a function of time, we can figure out what the induced electromotive force will look like over time, since it is equal to the negative of the slope. Let's say the flux was a triangle wave, such as the one shown here. If we look at just one section at a time, we see that the first line has a negative slope that is constant. Since the induced EMF is the opposite sign of the change in flux, it must be positive and constant. As the slope changes direction, so does the induced EMF, and so on. Let's look at another example where the function for our flux is a sine wave. We now have a more complicated slope. If this is a sine wave, it means that the derivative is a cosine. We take the negative of that derivative, and we get the negative of a cosine curve for the shape of the induced EMF.